section 12.5. In section 12.5, we're going to look at common and natural logarithms in this section. Coming out of sections 3 and 2, we talked about in section 12.2 about exponential functions. And in section 12.3, we talked about the logarithmic functions. So here we're actually going to take a look at a couple of very special logarithmic functions. One of them is the common log and the second one is the natural log. So that's what we want to talk about in this section. So here is again the page of the exercises that you will be looking at. Again, the ones that are in highlights, yellow highlights, are the ones that you actually will be doing for your homework. And I'll do problems very similar to these as we go through. And this exercise right in here, let me show you this one. You're actually doing this exercise right in here, log 7. This is exercise number 11. Okay, that's just this section we're going to use heavily calculators. So we're going to rely a lot on calculators to help us do our computations. We're not going to do anything by hand, so we definitely need a calculator. And for my graphs, I'm going to be doing them by hand, some of them. And then we go to Desmos and we actually take a look at better graphs in Desmos. Also for calculator input or entries, I'm going to use a TI-84 emulator. An emulator is like an identical copy, right? It's just a software run of the calculator. So the emulator actually imitates the calculator, but only on the computer. Okay, so we're going to take a look at that. I'll show you how I do that. But you don't need an emulator. Okay, you just need your own calculators. Now, whatever calculator you use, it may be different than a TI, so make sure you have your user's manual or user's guide for the calculators that you use. So let's go ahead and start. The first base we're going to look at is a base 10 logarithm. Now, these base 10 logarithms are commonly known or called common logs. And they're common in the sense that they are the same as our base 10 decimal system. So in that sense, they are common. Now, if the base of the logarithm is 10 and it has to be 10, nothing else, it's got to be 10 right in here. If the base of the logarithm is 10, therefore we call this a common logarithm. And we are actually allowed to leave the base out. Notice in here. So that's the form that we actually want to go to, the form that leaves the base out. Okay, and so this is a common log. Now, as an example here, let's say I want to evaluate log 15 base 10, and we can write it as a common log, just a log of 15 without the base. Remember, if the base is left out, it's implied to be 10. They just don't write it. So using a calculator, you get 1.1761. So let me actually go to the calculator now and I'll show you. So remember, we're doing common log of 15. So on my calculator, here's my emulator. This is the TI-84 Plus. And I was going to do log of, let me go back and just to refresh myself, it was log of 15. Okay, so for log of 15, it's actually pretty simple. I'm just going to hit log and then 15. 1, 5, enter. And then, of course, right in here, you can see the answer is 1.17091259, blah, blah. Now, in these exercises, the book asks you to find these answers to 4 decimal places. 4 decimal places. So in this, I'm looking at the display on the right side here. So I'm looking at 1, 2, 3, 4 decimal means right in here 10 thousandths. The digit to the right of that, if it's 5 or more, you round up. If it's less than 5, you round down. In other words, you just leave it alone. You don't do anything. if the number immediately to the right of this is 5 or more, you round up. So this is going to be 1.1761, right? And if you look at my notebook, that's what I have. So that's how I got it, using a calculator. Pretty simple. Now, next we're going to talk about a log whose base is e. First of all, number e. Number e is an irrational number, just like pi is. And the approximation for e is 2.71828118, blah, 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 blah. Now, this number is irrational. That means there are no repeating blocks of digits. Okay, so it does not terminate, and there are no repeating block of digits, which makes the number by definition an irrational number. Now, a natural log is a logarithm whose base is e. Okay, so that's all that is. So this time, if the base of the logarithm is e, right down here, then we call this a natural log. Now, remember, for common log, right up here, common log, if the base is 10, they don't write it. Well, if they do the same thing with natural logs, if log x base e, if they just don't write base e, then there's a confusion with common log versus natural logs, correct? So for log base e, they're going to actually use the ln notation. This is L, this is n. And in fact, we read this as ln of x. ln of x. Like Ellen DeGeneres, this is ln, but ln of x. Now, this ln of x is also known as the Naperian logarithm in honor of John Napier. Remember, we talked about that in, I believe it was section, maybe earlier sections. Yeah, in section on logarithms, I mentioned his name as the person who discovered logarithms. So, in his honor, he did not name it in his own honor, but later on, in his honor, a log base e was called the Naperian log. Now, the reason that it's called the natural log is like, what is so natural about it? Well, the natural log of x is used quite often for modeling growth of bacterias, certain type of bacterias in biology. So because of that, they call this natural log, because it is studied quite often as a modeling device or tool for biological studies. So just want to point that out, why they call it natural log. Now, to do an example of a natural log, so I'm going to look at ln of 1.9, and that number is 0.6419, ln of 1.9. So let me go back to my calculator here, 1.9. So I'm going to clear this one. And now, for the natural log, the ln is actually directly below the log button. So it's right in here. That's ln of, and it was 1.9, so just type 1.9. And you can also see it in the display here on the calculator itself, or on this table to the right of it. You can see that. Okay, no need to close parentheses, but I'm going to close parentheses just to look nice, and then hit enter. And there is a number again, rounded to the nearest 10 thousandths, 4 decimal, that's 6418. This number to the right, immediately to the right of 8 is 5, so we're going to round up. This is going to be 6419, and that's how I got my answer of 6419. Now, we'll see in a moment. In fact, again, let me go back to my notebook, and I made up a couple of examples in addition to this one. ln of 0 and ln of -2. Now remember, for all logarithms, the argument of the log, that means x, what sits in front of a log that you want to input in the calculator, this has to be positive. If it's 0 or negative, then it won't work because it's undefined for those values. So I'm actually going to do that on the calculator to show you how it's going to complain about it. I went in and wrote the answer for ln of 0, undefined, -2, undefined. Usually that's how we answer it. But let's see how the TI calculator is going to respond to ln of 0 and ln of -2. So I'm going to go here, and let's type in ln of 0. Okay, enter. You see that? It didn't like it. And actually in here, it gives you some kind of explanation. It reads, value entered is not allowed in the function or command. Okay, so I'm just going to quit that. So ln of 0, remember that one, we got an error. Oh, up here actually it does say error domain. You see that? Right up here. So in other words, you put a number that's not in the domain. So it's giving us a hint for that. So let me clear that. Next, I'm going to do ln of -2. So that's going to be ln of parentheses. Ooh, double parentheses. I didn't want to do that. -2, close paren. And check this one out. See this one now? Again, for this one is interesting. The error is different now. The error message right up here. The error message reads, non-real answers. In real mode, all calculators must result in a real number. So anyway, because again, we are not in the domain. So that's how TI responds to this kind of error. I'm going to clear this one. And in fact, let's clear all of these now. Okay, and let me go back to my notebook. So that's how we found these numbers. Now, the question might be is this. Well, what if the base of the logarithm I'm working with is not 10 and the base is not e? In other words, I'm not working with a common log and I do not have a natural log. So for example, I could have a log base 7. How do I do these on the calculator? Well, some calculators actually now are capable of handling any base, logs in any base, any valid base. And the valid base, remember, base must be positive and it cannot be 1. So, but just to illustrate how we're going to do this, the answer to the question is, of course, change of base formula. And here's what the change of base formula tells us. That log in any valid base b of m could be written as log of m over log of b. But the catch here, or the key here, is that the base here, a and a, these must be the same bases. So we cannot use two different bases. And for most parts, we're probably going to do what? Common logs and natural logs, right? Otherwise, we cannot use our calculators. So let's take a look at an example how this is done. So this is exercise number 36. In exercise number 36, they want us to use the change of base to evaluate this logarithm. This is log base 6 of 37. So I went in and wrote it as log 37 over log 6. Remember, the base is not there. That means I'm thinking common logs, right? And they mention it up here also. Right in here, right in here, they say you can use common log or you can use natural log. And so I use both of them. Here, this is with the common log, and then directly beneath it is the same ratio only with natural logs. And I went ahead and put in the numbers, and those are the answers that I got. You can verify these on your calculators. Okay, so if you note in here now, you can kind of see that these two answers are the same, and they have to be. Because again, the change of base doesn't care what base you use. So you can use common log, natural log, whatever base. Okay, so there is your number 36. Now, something in the way of famous or important logarithms. So we talked about common logs and we talked about natural logs. Those are the two that are in this section of your textbook, but give you a little extra for your money here. Actually, in computer sciences, they use log base 2 quite often. They use it for a lot of reasons. For example, they may use it to establish the efficiency of the algorithms. Computer algorithms. But in their work, they actually use base 2. I guess base 2 relates to computers nicely because of the 0-1 nature of computers, right? The processors and all that. So log base 2 is what they use in their textbooks, and they actually call a log base 2 Logarithms, and that's what I have right in here highlighting for you. Logarithms, which sounds pretty interesting. And how do they write it? This is how they write it. They write it as LG right in here. Remember, natural log is ln, common log is log with no base. Well, the computer scientists said, why don't we do the same thing? They removed the O in log and turned it into a log, Lg of x. And in fact, that's how they read it. So, those are the only ones that I can think of that are actually famous and are used quite often in textbooks. So anyway, now I'm going to do some exercises here with you, very similar to the homework problems you're going to be doing. So in exercise number 12, you want to do log 2. Number 22, we're going to do 10 to 0.59. And there you go. These are the ones that we're doing. Okay, so let's take a look at exercise number 12. I'm going to do these actually using the TI calculator. Okay, so for log of 2, I'm going to have to toggle back and forth. So I apologize for switching back and forth between the screens because I want to show you on the calculator. So number 12, log 2. Let's do that one. So I'm just going to go log 2, enter, and there you go, 0.3010. Good enough. 0.3010. Number 22 actually is not logarithm, is 10 to a power. 10 to a power of 0.59. So 10 to a power of 0.59. Let's do that one. So I'm going to go 10. And here the caret or hat sign, there you go, to the power of 0.59, enter. That's 3.89 and change. And I believe also you can also do the same thing, second, and then log gives you 10 to a power, you see that? And then just put 0.59. So two different ways you can do it, and you get the exact same results. So one I use the function, the preset function here. The other one I use 10 and the caret sign, the hat sign. And that's the answer, 3.890. Now to 4 decimals, remember to the right of 4 lies a 5. So we're going to round this up to 3.8905. And there you go, that's what I got. Number 32 is e to 3.06. E to 3.06. E, so that's going to be second, ln, there you go, E2. And it was 3.06, right? 3.06. Hope that was the right one. 2132.76, rounded, correct? 2132.76. 2132.76. That's number 32. Let's do number 34. In number 34, it's kind of like 32, except it has a negative exponent. I just want to show you how negative exponent is done in TI, if that's what you use. E to negative 2.64. So we have e to negative 2.64 and enter. And that's e to negative 2.64. 0.071, and again, because we rounded to the nearest 10 thousandths, 4 decimals, digit to the right of that 6, 5 or more, you round up. So that's going to be 0714. And here is 0714. Now in number 42, again, we're doing one of those change of base formulas. Log 25 in base 0.25 or log base 0.25 of 25. So you're welcome to use common logs or natural logs, and I use both of them, and I checked, the answer turned out to be that. Now to do this on the calculator, ln of 25 over ln of 0.25. ln of 25 divided by ln of 0.25. You see that? Enter. Ooh, didn't like the syntax. No worries, we'll fix it. Let me clear the screen. Okay, ln of 25. Close parent. The problem was with parentheses here. ln of 25 divided by ln of 0.25. Let me close parentheses. Now you see how that looks reasonable. That should do. The answer is negative 2.3219. Okay, 3219, and there's 3219. So this is how you work these. Notice again, everything you need a calculator in order to be able to do it. Now let's actually take a look at some of these graphs. So what does a graph of log and natural log look like? Now remember, the base of both of these is greater. Base of common log is 10, base of natural log is e, which is almost 3. So both of these are going to look like the general any logarithmic function whose base is greater than 1. So let me actually now go to Desmos. And, sorry, there you go. I'm in Desmos now. I've already here listed some logarithmic and exponential functions that we're going to look at their graphs. So first of all, let's take a look at the graph of log of x. And there you go. This is what this graph looks like. And you can kind of see that. And remember, all logarithms, unless you shift them to the right, left, up, down, they all go through this point 1, 0. Excuse me. So this is a graph of log base 2 of x. What does a graph of log base e of x look like? There you go. As the base increases, this portion of the graph actually lies below the one with the smaller base. And instead, what's less than 1, between 0 and 1, the value actually, this curve lies to the left of the one with the smaller base. A log base 10, check this out, the green. See how this one now lies, this portion above 1 lies below the other ones. And for between 0 and 1, the curve lies to the left of the other two. Now let me take log base 2 out. Okay, now you can kind of see how these two logs look like. And let me just kind of first shrink it, and there you go. And the one on top is natural log. Oops, I don't know what happened here. There you go. The one on top is the natural log, and the one on the bottom is common log. If you enlarge it, oops, sorry, there you go. If I enlarge these, then you can see a better graph. Oh, there's actually one here now. The one appears on the tick marks. So green is common logs. Okay. And let me go back to my note. So those are the graphs we just saw. Now in the ladder segments, near the end, we're almost near the end. In number 50, try not to look at the other ones. In number 50 here, we're going to graph e to the x plus 2. You can all do all of these in Desmos for you. So the graph of e to the x plus 2. Well, this is the graph of e to the x. It's going to look like this. An exponential function. Remember, the base is 2.7, almost 3. So it's going to behave like almost 2 to the x or 3 to the x. We study these graphs in chapter 12, section 2. It was exponential functions. Now, the effect of plus 2 here is to actually translate the graph of e to the x up 2 units. Okay, so and that's what's happened in this graph. Now remember, this point is 1, moves up to 3. Now, the floor that goes with every exponential function, this floor is actually at the x-axis. This is for e to the x. This floor, the floor also moves up 2 units, 1, 2. So the new floor is now up at a height of 2. Okay. So this is the graph of e to the x plus 2. Let's go to Desmos. And let me deactivate these. So here's a graph of e to the x. Okay, and there it is. Notice how this graph goes through point 0, 1. Now the graph of e to the x plus 2, it's going to be a vertical shift. And by the way, also, please note that the floor underneath is the x-axis here, right? This is the floor underneath. Now, e to the x plus 2, I expect this point, which is at 1, 0, this point, almost, there you go, 0, 1, I mean, it's going to move up to 0, 3. And there you go. And let me change the scale so you kind of see. This is what the top graph is the answer, the one in red, e to the x plus 2. Okay. And that's what that one looks like. Now, let's take a look at another graph. Number 64. This one is the graph of natural log of x plus 3. Now, the natural log, again, that's log base e, which is almost 3. So it's going to look like the graph of log base 3 of x. If we graph these logarithmic functions, base 2, 3, 4, and so on, base 10 even, if I remember, in section 12.3. So this is the general shape of the natural log. That's a log base 3 almost, 2.718, blah, blah, blah. And then the effect of 3 again is to shift everything, the graph, everything moves up 3 units. So the point that's on the x-axis has a y of 0, now moves 1, 2, 3 to the height of 3. And likewise, the entire graph, all points, move up accordingly 3 units. So that's ln of x plus 3. Let's take a look at it in Desmos. And this is the graph of natural log of x. There it is. Okay, so that's natural log of x. Now ln of x plus 3, and this point I want to make sure you see that point is 1, 0. This point is going to move up 3 units. So I expect it for this point, this particular point right in here, to go right up here. It's going to end up in here. Okay. And there you go. Again, notice the point that was in here. This one, 1, 0, is now at 1, 3. It moved up 3 units. And likewise, everything moves up 3. This point, up 3. This point, up 3. Everything. This point here goes up 3. Okay, and this is kind of how they look. And let's take a look at our next one. This next one we're going to look at is number 70. The graph of negative natural log of x. So again, I started by graphing ln of x in general form without plotting points. The effect of negative in front is to cause a reflection about the x-axis. So it's going to flip it over. This 0.01 is not going to change. So let's graph this in Desmos, ln of x, and then negative ln of x to see how it's going to look like. So, well, this is what ln of x looks like, right? We already looked at that one. This is a graph of ln of x. Now, negative ln of x, oops, what did I do? Okay. Negative ln of x, look at the reflection here. Well, there you go. And negative ln of x, boom, there you go. So all the points are reflected, in fact. So the reflection of, let's say, this point is here. The reflection of this point is here. The reflection of this point is up here. And of course, a point that is on the x-axis, because you're reflecting about the x-axis, so any point that's on the x-axis has its own reflection on the x-axis. That's why this point that is 1, 0 right in here, this 1, 0, actually for both graphs go through that. Now remember, we actually want negative ln of x, so this is the final answer to the graph of negative ln of x. This is what it looks like when you look at large scale. Now if you just kind of focus in the neighborhood of the origin, then this is what the graph looks like. Remember, we don't want to plot points here. We just want to do a general graph, knowing the general pattern of what it looks like. And you can see I haven't plotted a single point on any one of these. Now, this is our last exercise, number 72, 74. And again, you're not doing it most of these. You're doing just a couple, I think. I'm doing more just so you kind of see how this is done. It's good to see more varieties. So, this time, I'm doing number 72, 74 together. Number 72, ln of x plus 1, 74, ln of x minus 3. Now, the number that's within parentheses usually causes a horizontal shift. Okay, so x plus 1 is this one. There will be a shift to the left 1 unit. So even the vertical asymptote moves to the left. For ln of x minus 3, it actually moves from here to the right. So what used to be a 0.10 on the graph of natural log of x becomes 0.40 on the graph of natural log of x minus 3. So going back 1, that's for this one, and going to the right, a horizontal shift in both cases. And we're going to do those in Desmos, ln of x plus 1, x minus 3. And I have done those, see? So let me go back. This is just ln of x, remember this one? We actually want to shift these to the right or left. So let me, there you go. So ln of x plus 1, look at what's going to happen to the graph. It shifted to the left 1 unit. The vertical asymptote used to be the y-axis for ln of x. Now it's actually x equals -1. For x minus 3, that one moved to the right. You see this one? Let me deactivate the other one. There. So again, the one on the left, this blue curve, that's ln of x. And the red is ln of x minus 3. So 1.10 goes 1, 2, 3 units to the right, and you just redraw that. The vertical asymptote, that's the y-axis, means the line x equals 0. Also moves to the right 3 units. So it's now at x equals 3. And there you go. Now you have all 3 of these kind of working together. The one on the left is ln of x plus 1, this one. In the middle is ln of x, and to the right is ln of x minus 3. And with that, we are done with section 12.5. And we only have one more section to look at, so we're going to do that in the next section. We're done.